prove that for any n, any positive integer greater than 2, n to the n plus 1 is greater than n plus 1 to the n. Okay, so what am I thinking first here? First thing I'm thinking now that I actually write this out is maybe if I expand the right-hand side, with the binomial theorem, then the leading term, if I expand this out, will be n to the power of n. And on the left-hand side, I have n to the power of n plus 1. But of course, I'll have all the remaining terms on the right. And I would have to show that the extra exponent here kind of makes everything bigger than that. I'm just going to write out for some specific values of n what this looks like. So let's see what happens if n equals 4. I have 4 to the power of 5 on the left. And on the right, I'm going to write this as 4 plus 1 to the power of 4, which is 4 to the 4 plus 4 times 4 cubed plus 4 choose 2 times 4 squared plus 4 times 4 plus 1. And what does 4 choose 2? 6, right? Okay, so let's replace this with a 6. Okay, so I'm comparing now, for this case, for this value of n, I have 4 to the power of 5 compared to 4 to the power of 4. So yeah, the leading term here is clearly smaller than what I have on the left-hand side. Maybe my strategy should be to make everything here strictly larger so that these two quantities become equal. Well, on the right-hand side, if I replace the 1 with a 4, then I can factor a 4 out of the right-hand side. I don't know if that's going to help. I suppose the way I've written this is actually n minus k, which is n to the n plus this sum. K goes from 1 to n choose k of n to the n minus k. And I want to compare this to n to the power of n plus 1. Okay, well this is less than n to the n plus sum as k goes from 1 to n minus 1 of n choose k, n to the n minus k plus n. This is exactly what I'd said before. This is just replacing this last trailing 1 with n. Ooh, what if I increase everything on the right hand side so these powers become the powers here match the power there. So so what I'm saying here is change every term in the sum here so that I have n to the n, right? I've made each of these exponents is now larger. So I've increased everything in going from here to here. And in fact, there's nothing special about the first term here. This is just sum as k goes from 0 to n of n choose k. And this is when you have the sum of all these combinatorial terms, right? This summation is equal to, you think, well, this is the total number of subsets of n elements, which is what, 2 to the n, right? I don't know if this is going to give me what I want, because like I wonder, let's test whether this works for a few values of n. So again, if n is equal to, let's say 4, then I have 4 to the 5, and this thing on the right is 4 to the 4 times 2 to the 4, which I'm not sure actually will be less than 4 to the power 5. I think this is a little bit too much. This is making things over here a little bit too big. We need a little bit more precise control over how big this thing is. I might come back to something like that, but I had another idea as I was going through here. I know that this thing is only defined for integers greater than 2. But I thought about maybe defining a function like this. So I'm basically taking these two terms, putting them on one side of the equation, and showing that maybe it's monotonic. So what happens if I take, let me write this as a sum of two functions, because it'll be easier to differentiate these separately. Okay, so g of x is x to the x plus 1, and h of x is x plus 1 to the x. So I want to take derivatives of both of these things. And the easiest way to take derivatives of g and h is with implicit differentiation. So log of g is x plus 1 log x. So if I take a derivative of this, I have g prime divided by g is log x plus 1 over x. So g prime is g log x plus g times x plus 1 divided by x. And g is x to the x plus 1. And this simplifies a little bit here. Okay, let's do the same thing for h. So log of h is x times log of x plus 1. So h prime divided by h is Okay, putting everything together here, I have f prime is equal to x to the x plus 1 log x plus x to the x times x plus 1 minus x plus 1 to the x log x plus 1 minus x plus 1 to the x minus 1 times x. Can we simplify anything here easily? So I think trying to show that this thing is always positive or negative or something like that is going to be no more or less difficult than just trying to show the original inequality. So I mean, I think an approach more along the lines of what I've been trying down here might be better. Let me see if I can go back to trying something like that. Okay, so we have n to the n plus 1, and we have n plus 1 to the n. Right, I have one more idea for this question before really giving up on it. But I'm going to see if I can try and prove the result by induction. I don't know why I didn't think of this before, but if it's not, if this doesn't work, then I'm actually pretty stumped as to what to do. Okay, so we're going to assume that this is true for some value of n. The base case we need to check is when n is equal to 3. We've kind of done that already. So we have 3 to the 4, which is equal to 81, and 4 to the 3, which is equal to 64. So it works for n equals 3. And now we need to try and prove that it's true for the value n plus 1. So we have n plus 1 to the power of n plus 2. And I want to write this as n plus 1 to the power of n plus 1 times n plus 1. Will this end up working out? Well, I don't know. We might have to do a lot of manipulation of things here. Maybe it's best to write this as n plus 1 to the n times n plus 1 squared. I don't know. Because here, well, there we have this term, but that's not really, that inequality is kind of going the wrong way. Okay, well, so if I can make this thing, if I make the right-hand side smaller and turn it into this, then I'm done. Sorry, I need to turn it into, what am I aiming for? I'm aiming for n plus 2 to the n plus 1, but I'm allowed to use this inequality. So there's an n plus 1 to the k here. Let's write this as n plus 1 to the n times n plus 1 to the k minus n. So n plus 1 to the n, so we can replace this with n to the n plus 1. Here I have n plus 1 to the k minus n. I don't see how I'm going to get an n plus 2 anywhere out of this expression. This is really stumped me. I don't know if I'm missing something extremely simple here. Yeah, I'm gonna have to have a long think about this one. If anyone has any ideas, let me know. Thanks for watching. All right, so I've been thinking about this problem a little bit for the last few hours on and off. And I think I've actually come up with something that will solve this very easily. I'm surprised that I didn't actually think about this earlier. And if you've watched one of my previous videos about solving for all values of a to the b equal to b to the a, we're going to do something very similar to what I did there. This expression is very similar to the inequality that we're dealing with in this question, so it's not really a surprise that something similar is going to come out of this. And I'll link to the video for where I solved that question, or at least got through most of the solution to that question, so you can see what I did there. So what we're trying to show here is that n to the n plus 1 is greater than n plus 1 to the n. This is equivalent to showing that the logarithm of the left-hand side is greater than the logarithm of the right-hand side. So the logarithm function is strictly increasing. So if this is greater than that, then the logarithm of this is greater than that. And this is an if and only if statement. So I can write the thing we're trying to prove is the same as this. And by some rules of logarithms, this is the same as n plus 1 log n greater than n times log of n plus 1. And now I'm going to divide by, I'm going to rearrange this equation. Everything that I'm dividing by is positive, so there's nothing about the inequality sign that has to change. All right, and this is the inequality that I'm going to prove. And if we just go back through the sequence of steps here, go up this way and across that way, then if I've proven that this is true, then I've proven that the original result is true. Okay, and now you can see the similarity between what I'm going to do here and the approach that I took in this previous question about a to the b equal b to the a. So what I'm going to do is define the function f of x to be equal to log x divided by x. And all I'm going to do is show that, in fact, in the previous video about this question, I defined a similar function and I showed that this function has a maximum at e. And so essentially what I conclude is that this function is decreasing if x is greater than e. But I'll go through the steps of showing that again. The way I'll do this is by computing a derivative. Okay, so the derivative of my function is given here. This says that f of x has a maximum at x equal to e, because the derivative will be equal to 0 there. I mean, I suppose technically all we've done is shown that there is a local minimum or maximum at that point, but you know, if you compute some limits of this function for values of x approaching 0 or infinity, then you can conclude that this is in fact a maximum at x equals e, and f is decreasing for x greater than e. All right, so if x is greater than e, the denominator here is always positive, the numerator here will be negative, so f is decreasing. And what does this say? This says that f of x1 is greater than f of x2 if x2 is greater than x1. Okay, this is what it means to be decreasing. So now if I go to the values of x I'm actually concerned with, n and n plus 1, well, this says that f of n is greater than f of n plus 1. But let's just substitute now what f is actually equal to. This says that log n divided by n is greater than log n plus 1 divided by n plus 1, and we know that this is equivalent to the statement we're actually trying to prove. All right, so I suppose the only sort of little loose end to tie up here is that in the original question, we were asked to show that this inequality is true for n, an integer greater than 2. And so what I've done here is I've actually shown that this inequality holds. N doesn't have to be an integer. It can be a real number. It just has to be greater than e. But the smallest integer greater than e is 3. And so, you know, this condition is satisfied by all the values of x greater than e. So yeah, really straightforward in the end. Just recognizing that rearranging this inequality, I'm kind of surprised that I didn't end up doing this myself. There were some times earlier in my solution where I was close to doing something like this. I had some similar expressions to this written down earlier, but for some reason just didn't go ahead and define this expression and think of it as a function of n or a function of x. Doesn't really matter in this case. But there you have it. Really straightforward question once you sort of take the right perspective. Thanks for watching.